Our speaker today, Dr. Neil Daswani, has held a variety of responsibilities of research, development, teaching, and managerial roles at Google, Stanford University, Docomo, USA Labs, Yodlee, and Belcor. His areas of expertise include security, wireless data technology, and peer-to-peer systems. He has published extensively in these areas, frequently gives talks at industry and academic conferences, and has been granted several U.S. patents. He is the principal author of the book, Foundations of Security, What Every Programmer Needs to Know. Neil received his PhD and master's degrees in computer science from Stanford University and earned a bachelor's in computer science with honors with distinction from Columbia University. Dr. Neil Daswani.
Thank you very much for the introduction, Joel. So I'm going to be talking about what every programmer needs to know about security and where to learn it. One of the places to learn some of it is in a book that I recently published entitled Foundations of Security, What Every Programmer Needs to Know. I'll have a copy that I'll be raffling off at the end of class today. Over the course of the talk, I'm going to be mentioning various information resources. You can find those at my website, listed on this slide, as well as on a website that I'll mention at the end of the talk. Of course, if people have questions throughout the course of the talk, feel free to just raise your hand and I'll do my best to answer. So let me just start off with a little bit of motivation. Over the past few years, I've been monitoring press releases about vulnerabilities that have affected real users and real systems, and after looking at these press releases for the past couple of years, sometimes I wonder whether or not the sky is falling. To look at two representative examples of some rather spectacular data breaches that have occurred, I'll first mention the TJX vulnerability, which was announced earlier this year. So TJX is a company that owns TJ Maxx, Marshalls, and a number of other retail department stores. The bad guys were able to steal 45.7 million credit card numbers from them by driving up to the retail branches, parking their cars outside, and monitoring traffic that was transmitted over the Wi-Fi network. While they were using a protocol called WEP, the Wired Equivalent Privacy Protocol, to attempt to protect those communications, the problem is that this protocol has been known to be broken since 2001, 2002. It has a vulnerability in how the RC4 stream cipher is seeded, and because of this vulnerability, all the bad guys need to do is gather enough data packets to work backwards and figure out what was the initial state of the table, and basically they then get all the credit card numbers. Another spectacular data breach that happened about 2 years ago to the Card Systems company. Card Systems was a credit card payment processing company. When you submit your card to a point of sale station, that card number goes through a couple back-end gateways as part of the verification process. Card Systems was one of the companies that helped in that process, and well, basically they fell susceptible to an SQL injection attack in which they had a database of about 43 million unencrypted credit card numbers. What somebody at the company did was connected a website to it, which had various forms that allowed users to authenticate, choose accounts, email people, and whatnot. Of course, the attackers entered database commands into those web forms and were able to drop a script on the backend database which would email them a couple thousand credit card numbers every day. And they were able to run the script for about 6 months until Card Systems even noticed. So they were able to get away with stealing 263,000 credit card numbers. Of course, there were 43 million that were exposed to the attack, so all 43 million customers needed to be notified. Visa and MasterCard canceled their contracts with the company. The company fell under FTC investigation, and needless to say, they're out of business. So while 2005 seems like a long time ago on internet timescales, one thing to keep in mind is that SQL injection attacks have still occurred quite frequently. In fact, if you go to a site like news.google.com, type in SQL injection, you'll just see article after article of recent vulnerabilities due to this type of attack. Data breaches like this have occurred a lot over the past couple years. There's a site called privacyrights.org, which has been maintaining a pretty good chronology of all of these types of data breaches. Since 2005, there's been about 153 million compromised customer records of some kind, and in 2006 there were 300 incidents alone, which means one incident per business day. So there's a lot of work ahead of us in securing cyberspace, but basically from these issues, I hope you can see why I feel that the sky might be falling, and if it's not falling now, it might be falling sometime soon. So what I'm going to do in this talk is tell you about some high-impact threats and how to defend against them. I'll talk about SQL injection and cross-site request forgery. How many of you have heard of SQL injection? About half. And how many of you have heard of cross-site request forgery? Just fewer. So I'll talk about these particular threats, and then I'll talk about some vulnerability trends, and finally, to wrap it up, I'll tell you where you can learn more. So how did this attack at card systems happen? How does SQL injection work? Let me go ahead and provide a simple example of how this type of attack can happen within a two-tier web architecture, where one tier is the web server itself, and the second tier, of course, is the backend database. So you can imagine that a user might want to log into a web server or a web application rather with a username and password, and what the web server or the web server application might do is, given that username and password, it might want to check if the user is authentic. The way it does that is constructs a SQL statement, a database command, which says, tell me what the password is for the user name that was supplied. The SQL query might look something like this: select password from users where uname is equal to the username that the user supplied. So $username in this case is a variable that gets filled in with whatever the user inputs. Well, you could imagine that the way that an attacker might take advantage of this is, instead of entering a regular username, an attacker might enter a username like quote semicolon drop table users semicolon hyphen hyphen and enter something for the password. Really doesn't matter what. But if this is the username and this gets plugged into the database command, you could see how this good query now becomes a malicious query. The malicious query becomes select password from users where the username is, the quote closes off the username. So it's a blank username, semicolon. The first statement gets closed off with the semicolon, and the rest of the input makes up a second statement, which drops the users table from the database, basically eliminates the record of all the users. So this is what's called a denial of service attack, where any user that tries to log in after this malicious input was provided will not be able to log in. Now, of course, the website could recover their password database from a backup, but that's pretty much inconvenient. By the way, the last two hyphens is absolutely required. What it does is it comments out the quote that the application provided. In any case, you could see that it's possible to provide the right tweaks to the SQL statement to make sure that it actually gets executed. Now, when you're looking at this kind of an attack, you might think, well, you might think, oh, well, what I could do is just filter out quotes, right? That should solve the problem. Or look for other characters like semicolons and make sure I just filter those out. And while that might be a good first attempt, it's completely possible to do an attack where even if your web server application is trying to filter out malicious input, it can still fall prey to an attack. So in this slide, I've provided a simple example of a website that might be selling pizzas for a living. It might have a page which allows the user to look up the order history of all of the pizzas that were ordered, and the user might choose the month. So in this case, January might get chosen, and you could see all the pizzas I ordered in January. The HTML for this kind of a form might look as follows. It might have a form on it that has a select block. The select block has a couple of options. There's an option basically for every month where the option has a name, month, and has a value, 1 to 12, depending upon which month the user wants to see the order history for. And there's a submit button at the bottom. Well, of course, an attacker can take advantage of this in an interesting way. You could imagine that the SQL query behind a form like that might be as follows. It might be select the pizza, the toppings, the quantity, and the order day from the orders table where the user ID equals the user ID corresponding to the user that logged in, and the order month equals 10, if, say, the user wanted to see what pizzas were ordered in the month of October. Of course, an attacker has many options to still attack. What the attacker can do is choose 0 or 1 equals 1 to be the order month. So the attacker can just download the HTML, modify the value to be or equals 1 over 1, correct some things in the form, and resubmit it to the website. Now, what happens when this input gets submitted is the query will be as before, except at the end it'll say where user ID equals 4123 and order month equals the order month provided by the user, 0 or 1 equals 1. So, of course, in SQL, AND takes precedence over OR, and so the user ID equals 4123 and order month equals 0 ends up evaluating to false, but the OR 1 equals 1 part evaluates to true. And notice that there's no user ID specified. So basically, the result of the query will be all of the pizzas that were ordered for every user. So if an attacker entered 0 or 1 equals 1, the output that the attacker would get is a table as follows, which contains all of the pizzas, all the toppings, all the quantity, all the order days for all the pizzas that were ordered for all the users. Now, while this might not seem that bad for a site that allows you to order pizzas, imagine if this was a web service that allowed you to store your medical history, or if it had a lot of credit card numbers behind it. Well, this could be quite damaging. It basically allows the attacker to get all user data. In fact, let me provide just one more example here. So let's say it is a pizza delivery site, and I simply want to get access to all the credit card numbers that were used by legitimate users. Well, what I could do as an attacker is, for the order month parameter, I could provide the input 0 and 1 equals 0, union select cardholder number, expiration month, expiration year from the credit cards table. So what's going on here? Well, the 0 and 1 equals 0 will end up evaluating to false. And so basically the entire first part of the query evaluates to false and returns no results. But the union select cardholder number, expiration month, expiration year from credit cards will give back all of the credit card information for all the users on the site. Why does this attack work? Well, if you notice, in this particular example, cardholder number, expiration month, and expiration year, if you look at the types of those columns, the data types, they are chosen to exactly match the data types from the previous query. So the union actually works. And what the attacker will get as a set of output is the following. They will get the pizza order history table with the values corresponding to the credit card holders' names, the numbers, the expiration dates, and the expiration years. By the way, I should mention, while I've been demonstrating these attacks, you should not try these attacks on real sites for the reason that they may very well work, and we don't want you to get in trouble. And I certainly don't want you to get me in trouble for having told you about how these attacks work. So, where should you try these types of attacks? You should use them on test versions of, say, websites that you're developing for yourself, or let's say you're working for a company. Use them on a test version of your company's site. Don't even try it on the production version, because again, it might work, and then you'll see all this information. And if your company has to abide by SOX regulations, you might have just violated the SOX regulations by having engineers look at the actual data. So this is an example of a SQL injection attack. And now that I've told you about the attack, let me tell you a little bit about how you prevent these kinds of things. So we've seen that in this previous attack, let me just go ahead and go back for a second. In this previous attack, the information that the attackers supplied did not have any quotes whatsoever, did not have any semicolons whatsoever. And so this is an indication that simply trying to blacklist or filter out certain characters that you think might be dangerous does not work. Instead, an approach based on whitelisting might be desirable. So first of all, because attacks are possible where the attacker doesn't need to use any special characters. Even if the attacker did use special characters, you might forget to filter out some of them, and not others. Each database is different. Each of them have lots of different features. It's kind of hard to get the set right. But also, with things like quotes, there might be a user that's interested in having the username Brian. That could be a completely legitimate username. Why should you prevent the user from having that username? If your site wants to build a personal relationship with the user, you want to abide by their requirements, not your own. So blacklisting characters is generally not the best approach. Instead, an approach based on whitelisting might be better, where you can define regular expressions like the ones that I have here, and you could compare the user input to the regular expressions and only submit, say, the SQL query if the input matches one of the regular expressions. So if I'm expecting a month, I might use the second regular expression here. By the way, these are just examples. If we put in a couple minutes of thought, we could come up with much better regular expressions. Writing these kinds of regular expressions is hard. I'd encourage you to trade them with your friends and your colleagues and try to break each other's regular expressions. So using an approach based on whitelisting is better. And what you could do is, if your company or your organization is using a web application firewall like mod security, you could implement these kinds of whitelists using mod security and defend your website against these types of attacks by whitelisting. In addition to whitelisting, it might also be important for you to escape certain characters. So let's say you do want to allow the user to choose a quote as part of the input. Well, what you can do is use the database's escape functions, and each database has slightly different escape functions. So if you escape Connor, the database driver will give you back Connor, and basically the double quotes will be interpreted as a single quote data and will not be interpreted as control information. One of the running themes that you might see in attacks in the area of security is that the attackers might try to send in data that gets interpreted as control by the application, and that's absolutely a bad deal. You want to make sure that the database always interprets data as data. So another approach that you can use to prevent SQL injection attacks is taking advantage of prepared statements and bind variables. If we were to rewrite the backend a little bit differently, what one could do is have a query as follows, and call a prepare statement on a query template, where the query template basically provides the structure for the query and has question marks in places where we expect user data to get filled in. The purpose behind this is that by using these placeholders and then by later on telling the database driver, hey, set this first parameter to be the user ID, set the second parameter to be the month. If the attacker tries to specify a month that is, say, not an integer, the code will generate an exception. And the other thing that happens here is that the database will make sure to always interpret whatever you put in for the question marks as data and not control. So even if there was a quote in this input or an OR statement or whatever, it'll get interpreted as data and not a command. So that's another tool that can be used to fight SQL injection. What kinds of additional things can you do? Well, to the extent that you can, you should take a defense in depth approach. You should use as many diverse techniques as possible. One thing you could do is limit privileges. So you might not need to allow every user to be able to modify or delete data from the database. And so you could create a database user and have the web application log into the database with, say, a read-only account. So that even if someone is able to figure out a SQL injection attack, they're only able to read information but, say, not change it. Of course, as we saw in the previous example, even being able to read information can lead to very significant attacks. You should also make sure to harden your database server and your host operating system. So some databases, such as Microsoft SQL Server at some point, what it did is when the database comes to you out of the box, it has all kinds of interesting functionality turned on. It has functionality turned on that allows you to make outbound network connections. It has functionality turned on that allows you to execute command shells all from within SQL statements. But once you're launching an application into a production environment, there's no reason to keep those types of functionalities on. And in fact, it might be advisable that if your database application is using those types of functionalities to turn them off anyway and re-architect so that you're doing the actions on the back end in a more secure way. So I've told you a little bit about SQL injection. There is more to learn. For instance, second-order SQL injection attacks can happen when an attacker tries to get data put into your database, and that data later on gets used to construct SQL statements, and attacks can still become possible. I have some nice examples of this in the book. There's also blind SQL injection attacks, and the attacks that I've demonstrated thus far, the attacker needs to know a little something about the schema of the database in order to construct statements that can do successful attacks. And so blind SQL injection is a technique that attackers can use to, for instance, learn about the schema of your database by posing queries that will eventually reveal table names and column names and such things. Again, more examples of that in my book. So I've talked a little bit about SQL injection. SQL injection is a type of attack that can occur when input is not validated appropriately. There are other types of attacks in that category. Cross-site scripting, if you've heard of it, is another such type of attack. Not all, there's many types of vulnerabilities, there's many ways to categorize them. The second type of attack that I'm going to talk about is a cross-site request forgery attack. A cross-site request forgery can be considered to be a design error in a web application, and I'll tell you a little bit more about that. But there are also security vulnerabilities that can occur due to bad handling of boundary conditions, bad exception handling, improper access validation checks, etc. Before I start talking about cross-site request forgery, any questions? Okay, very good. I'm going to talk, so cross-site request forgery. The scenario that I would like you to have in mind is a scenario in which the user might be using one application, say bank.com, and by the way, I'm just using bank.com as a placeholder name. This is not really an attack against whoever the heck has bank.com. But think of a scenario in which an attacker is logged into some legitimate good service that's at bank.com, and the user logs into that service, say providing a username and password. The website checks the username and password. If the user is authentic, the website provides the user with a cookie that will be sent back by their browser on future requests to authenticate them. And in the scenario that I'm going to show you to illustrate how a cross-site request forgery attack works, the bad guy is going to lure the user to a site called evil.org and is going to be able to do bad things to the user. But the scenario you keep in mind is the user may have one browser window open to bank.com and happens to have another browser window in which they get lured to evil.org, and the attacker is going to be able to do bad stuff. I'll show you an example. So in this example, we have Alice interacting with bank.com. Alice might go to bank.com and be asked to log in. So Alice requests a login.html page. What bank.com sends back is a form that allows the user to log in. The user fills out the username and password. Say the username is victim and the password is FMD9032. And the web form might be constructed to make a call to a script on the server called auth. So basically, Alice's browser places an HTTP request for the auth script to be invoked and passes it the parameters, the username and password. Bank.com authenticates the user, determines it's a valid user, and sends Alice's browser a cookie with a session ID. The session ID is 40A4, etc. In this particular case. In a future request, Alice might then want to, say, check her bank balance. So Alice clicks some link in the site after having logged in and says, hey, I'd like to view a balance. And the browser automatically goes ahead and sends the cookie to bank.com because that's how cookies work. They're supplied on future web requests when the user goes to bank.com. And bank.com looks at the session ID, determines it's a valid session ID, and sends back a message to Alice saying, your balance is $25,000. Maybe Alice is a student, and this is the beginning of the academic year, and of course, over the academic year, that might go to zero. But anyhow, for right now, Alice has $25,000 in her account. So what can go wrong? So let's say that there's this other website in the picture called evil.org, and Alice somehow gets lured to evil.org. So maybe she clicks a link in some message in a news group, or clicks on a link in an email that she received. And there's many ways to lure Alice to evil.org, but let's say Alice gets lured to evil.org. Let's look at what evil.org might want to do to Alice. So as before, Alice requests the login page, gets back a form. Alice authenticates as before, provides the password, gets back a cookie after she's authenticated. Well, let's say after Alice has been authenticated to bank.com, say in one browser window, she gets lured to go to a page at evil.org in, say, another window. Well, Alice might request a document called evil.html from evil.org. That happens to be the document to which she's referred to. And evil.org sends back a web page that has a whole bunch of HTML on it. It might say nice things. It might get Alice to think she's at some good site or whatever it is. Part of the HTML on that page might be HTML that looks as follows. Image source equals http://bank.com/paybill, and then it passes some parameters. It passes the attacker's address. The address is 123 Evil Street, and amount is $10,000. So, Alice's browser gets back all this HTML, and of course, being a good browser, the browser wants to render the page for the user. So, I by the way simplified this. This might not be perfectly technically accurate, but it's simplified for the clarity of explanation. Basically, Alice's browser needs to render this web page. And in order to render this web page, the document has told the browser, hey, there's this image at bank.com I want you to go get in order to render this page. And this happens all the time on the web, right? People link in images from other websites and whatnot. So, so the browser says, oh, okay, let me make a HTTP connection to evil.org. Let me make an HTTP connection to bank.com. I have to access the paybill script, so let me go ahead and do that. Let me provide the parameters that were requested. And when the browser makes that connection to bank.com, the browser notices, oh, the user is logged into bank.com, so to abide by the cookie spec, I should go ahead and send the cookie for the user to bank.com as well. So bank.com gets a request from Alice's browser that says, Alice wants to pay a bill, and the bill should be sent to 123 Evil Street, and the check should be made out in the amount of $10,000. Alice's browser goes ahead and passes the cookie. Bank.com receives the request and sees a valid session ID and sees a request from Alice to pay a bill to the attacker, and goes ahead and does so, because it looks like a completely authentic request. So it says, okay, payment sent, done. So Alice just got duped out of $10,000 due to this cross-site request forgery attack. Basically, evil.org was able to forge a request, and bank.com goes ahead and abides by it because Alice was logged in. So if you've ever received the advice of only interact with one website at a time, this is why one might want to do that. If bank.com is susceptible to a cross-site request forgery attack and happens to get and the user happens to get lured, it could be game over. So one interesting thing here is that for those of you that know about JavaScript and how the web works, you know that there's something called the same origin policy. And that basically means that when say, an executable script is served to a user, that script is only able to access resources at the website that script came from. In this case, the evil site wasn't able to read any of the information on the bank.com webpage, but it didn't matter, because what the attacker was able to do is make a write request to bank.com. It basically made a write request saying, here, please post this request and issue this bill payment. So write-only access can result in considerable damage. What kinds of sites need to worry about cross-site request forgery? Well, any application that really has any user information, right? So Facebook is clearly an example where where this attack could potentially be possible. In fact, there was an attack against MySpace back in 2005 where the bad guy constructed a site profile for himself, which was architected such that whenever somebody visited his web page, it would automatically add them as a friend. Right? His site profile had some HTML which made a write request, back to MySpace, and basically it was architected smartly enough that if any of his friends' friends happened to visit, any of his friends' profiles, then they would also get added as his friend. So within like a 6-hour period, he got like 1 million friends, and MySpace had to shut down their site in order to deal with this problem. So cross-site request forgery can be quite damaging. How many of you have heard of drive-by farming attacks? Okay, a few. So drive-by farming attacks are yet another example of a cross-site request forgery attack in which, because of the fact that most home users don't change their default credentials for their wireless access points, bad guys are able to architect web pages that will go ahead and try to make write requests to addresses like 192.168.0.1 to change the DNS settings that the router happens to be using. And once the attacker is able to change your DNS settings, then it's kind of game over, because when your browser decides to make a request to bank.com, the DNS will tell it what's the IP address for bank.com. So the attacker can, of course, substitute whatever address he or she would like and take the user to evil.org, even though the URL bar will say bank.com. So for those of you that are familiar with drive-by farming attacks, they're just another example of cross-site request forgery at work. How do you prevent these kinds of attacks? Well, let me talk about a couple methods that won't work, and let me talk about a couple methods that will work. So one thing that, if you know about the HTTP protocol, you know it supports a referrer field, where every time that you get a request for a web page, every time that a web server gets a request for a web page, it gets a referrer header telling the web server what was the previous site that the user visited. Now, in our previous example, where the cross-site request forgery took place, bank.com's web server, when it gets the HTTP request to pay the bill, it'll get a referrer, and the referrer will be evil.org. Why? Because evil.org was the entity that sent back the HTML and/or JavaScript snippet saying, please issue this bill payment request. Unfortunately, web servers don't always get referrer headers, right? A user, for instance, that is using an HTTP proxy for anonymity, the proxy will go ahead and eliminate the referrer headers. So there's lots of legitimate reasons that referrer headers might get stripped out. So simply, if you want to prevent cross-site request forgery attacks, looking for the referrer header and only conducting the action that the user requested. If you see the appropriate referrer header, might not be the best approach. A lot of this won't work for a lot of your users. You might say, oh, okay, well, I'd like to use a web application firewall, something like mod security, like I did previously to prevent the SQL injection attack. Let me try to write regular expressions to look for dangerous input. Well, this solution doesn't work either, simply because there was no malicious input. From bank.com's standpoint, it's a completely legitimate request. It just happens to be issued by another site, not bank.com itself. So web application firewalls are not in the best position to prevent this kind of an attack. On the other hand, there might be some approaches that can work. So if, for instance, you ask the user to type their password again before issuing the bill payment, then that solution will work. Why? Because in order to forge a request, the attacker would then also have to know the user's password. But if the attacker knows the user's password, they could probably do a lot worse things as well. So this is an example where you ask for a user-provided secret, a secret that only the user and the bank.com site know, but that the attacker won't know. Validating the request by asking the user to provide a secret is a good way of preventing cross-site request forgery attacks. Finally, you can imagine that, well, this might be more inconvenient to users, and you might want an approach which doesn't require the user to enter the password again. So what you could do is use what's called an action token. And I don't have time to properly describe action tokens in all their depth, but the idea is that every time that bank.com gives a web page to the user, it will, in addition to all the information that's already there with regards to form that the users could fill out to submit actions, the server also generates a cryptographic authentication code that goes into that request that's created with a key that only the server knows. And then when the browser issues further requests, the server looks for that message authentication code. And so basically, if a attacker wanted to forge requests, it would have to know the server's key in order to generate an appropriate token to get past the check on the server. So using action tokens is another approach, and all of this is described in Chapter 10 of the book. So now that I've talked about two vulnerabilities in particular, I kind of wanted to step back, talk about some overall trends in the area of web application security, and recommend some areas where you can go to learn more. So this chart shows some information that I aggregated from a report that MITRE put out. And what it does is it shows the number of security vulnerabilities due to various causes that were reported between the years 2001 and 2006. And what we can see is that cross-site scripting, XSS, and XSRF for this purpose, I believe, is lumped in there. These types of attacks have been increasing dramatically over the past couple years. Attacks due to PHP include code injection vulnerabilities have also been growing. Attacks due to SQL injection, the upside down triangles, I know it's a little hard to see on the slide, have also been increasing. And then finally, DOS attacks and buffer overflows have continued to be issues, although they're not increasing at the same rate as these other vulnerabilities. What should you take away from this? Well, these types of attacks are increasing. I showed you some information from the MITRE vulnerability database, but there's many other vulnerabilities. For instance, Security Focus has a vulnerability database. I looked at a couple different vulnerability databases, but regardless of which one you look at, the big four types of vulnerabilities are about the same across the different databases. So cross-site scripting, cross-site request forgery, cross-site script includes, lumping all of these together are the #1 growing web-based vulnerability threat. Code injection attacks, for instance, SQL injection and PHP include types of attacks follow. And then, of course, memory corruption of various types, buffer overflows, integer overflows, format strings, and denial of service are also big issues. So these are the big four that you need to look out for when developing your web applications. What should you do? Well, if you're an engineer, a developer, a programmer, software architect, if you serve any of these roles in your organization, the first thing you need to do is you need to arm yourself. You need to make sure that you have a deep understanding of how these attacks work and how to defend against them. So I'm going to recommend a couple resources that you can go to learn more, and basically what you should learn. And then secondly, you should do things like for each project, for each software project, there's a lot of pressure to just get the application working and deployed. And so doing things like electing a security czar for the project might be a good idea, where that security czar takes on the responsibility of auditing the code and making the right decisions with regards to influencing people to watch out for these vulnerabilities. Let me get a little bit more specific. So I said arm yourself. Well, how do you arm yourself? What do you need to know? This slide shows what I think every engineer needs to know about security, and it's broken down into a couple parts. The first thing that I think every engineer needs to know about is secure design principles. Things like the principle of least privilege, fail-safe stance, how to secure the weakest link first. And it's important to have these principles in mind, simply because it's going to be impossible to teach everyone what each type of trick that the attackers play are, right? So actually, let me ask, how many of you got CS or EE degrees? Okay, how many are in the process of getting CS or EE degrees? Okay, more, good. And how many of you learned about object-oriented programming techniques like encapsulation, polymorphism? Good, very large number. And the reason that you learn these things is so that your code can achieve reusability, extensibility, scalability in some cases. How many of you learned about secure design principles as a requirement for your degree? Much fewer, like 3. Now, so these principles are important because they will, in a new situation, in a new scenario, they will help you derive what are the right things to do. I've talked about what are the big 4 web vulnerabilities today, but you know what? The big web vulnerabilities might be different tomorrow or the day after. And so it's important to have a top-down understanding of these things. So once you've learned about secure design, the next set of things to learn is, filling it in with experience, right? So for instance, in my book, I illustrate what happens if you don't follow each of these security principles with vulnerabilities in a web server. But you need to have a concrete experience with understanding, and so understanding what are all the different technical flaws that we've seen to date. I've talked about cross-site request forgery, but there's cross-site script inclusion. I've talked about code injection vulnerabilities. There's things like directory traversal, right? If you type in an URL with /////////////////////// password at the end, and the web server happens to be running at root and a couple other things are wrong, well, you might be able to get access to the password file, which might allow you to do a dictionary attack after that. Race conditions. Security vulnerabilities can occur due to race conditions. Time of check versus time of use problems, for instance. And of course, memory corruption. All of these different types of technical flaws can be used to conduct a variety of attacks. You can conduct data theft with cross-site request forgery. You can conduct data theft by using a SQL injection attack. You can do denial of service by taking advantage of a race condition vulnerability. So having a understanding of what these different threats are will help you figure out what kind of technical flaws you need to defend against. But I'd say this is probably the core of what every engineer needs to know. So where do you learn this stuff? Well, I'm going to provide a non-comprehensive list. Here at CERIAS, I think you guys are all lucky to have some very good faculty in courses, and I encourage you to take advantage of them. So I was chatting with Pascal Moiner earlier today, and he has lots of good materials, and I'm sure there's many other faculty who I haven't met with that do. You should surely take advantage of them. For those of you that are in industry and elsewhere, I'll provide pointers to some other courses. Most universities have cryptography as upper division courses, which is good, but an understanding of cryptography is only a small part of what you need to know to build a secure system. Many security vulnerabilities, in fact, most security vulnerabilities happen not due to vulnerabilities in the cryptography itself, but how the cryptography is used, or a mistaken protocol design. While there are cryptography courses at almost every major university, some universities, such as Purdue, such as Stanford, such as UC Berkeley, are offering system security courses that that teach you about software-related vulnerabilities. There's a more comprehensive list at Avi Rubin's website. Feel free to check it out. One of the things that's been frustrating is that very often, as part of undergraduate programs, as part of undergraduate programs, universities don't require that students take courses in security. And while I think some universities are taking steps in the right direction, this is typically an issue that companies have had to deal with after the fact. So, the chain is that students learn about computer science, they learn how to write software programs, they get hired by companies, they may not have taken a security course as part of their training, they write some code, that code gets deployed on the internet, it's now accessible to millions of people in addition to hundreds of thousands of attackers, and someone starts exploiting the vulnerabilities. And so there's various offerings that have showed up in the market that help companies train their software engineers to deal with these kinds of vulnerabilities. So I'll mention a couple of those. One of them that, in interest of full disclosure, that I helped co-found is the Security Certification Program at Stanford. It's available online anytime. You can take the entire certification program online, or you can come to campus for one intense week and take 3 required courses or 3 electives. In addition to lectures about how these attacks work, the program contains hands-on labs where you actually conduct the attacks and then write your defenses, all against test websites that have been built for these purposes. There's also a foundational certificate available as part of that, so if you have zero security background, it can help you build up to speed to the point where you can take the advanced courses. There's an URL here, you can check that out. The core courses in the certification program are how to use cryptography correctly, how to write secure code, and security protocols. Important so that you get a feeling for what protocols have been designed to date and what have been some of the problems. There's also electives in the management of computer security. Emerging threats and defenses is a course that can be repeated for credit every year and talks about every year the new threats and defenses that have come up. There's an elective on securing web applications. So there's lots of information there. There's some other security certification programs that are notable. One is offered by ISC Squared. They offer a certification called the CISSP. It's very good at preparing people for administration and government jobs in security. It's a credential that can be used if you want to do PCI compliance audits for a living. Basically, you pass a long multiple choice test. Another certification that you can get by passing a multiple choice test is the GIAC Secure Software Programmer, GSSP. It's offered by SANS. This is fairly new, and it focuses specifically on secure programming, whereas the CISSP is much more broad and covers 10 fairly diverse fields. So those are other certification programs. There's a variety of good books, one by yours truly, of course, Foundations of Security, what every programmer needs to know. There's also a couple of other great books. There's Ross Anderson's Security Engineering, which I actually recommend highly to everyone because it's free. Ross was able to work out a deal with his publisher where you can access the full contents of the book online. There's Viega and McGraw's Building Secure Software, which is often referred to as the classic text in this space. It doesn't focus as much on web application, but it does talk about buffer overflows and race conditions and all kinds of other attacks. And then, of course, if you're going to be writing security-sensitive code, I'd encourage you to check out the Secure Programming Cookbook. It has lots of code examples of how to do input validation correctly, of how to call the OpenSSL libraries. Using cryptography can be very fragile. If you provide just one incorrect initial value, the entire security of your scheme can go through the floor. So you can check out that book as well. There's a number of very interesting websites. The OWASP website is one of them. It stands for Open Web Application Security Project. One nice thing about the OWASP is they have a chapter in almost every major city. There's the Security Focus website, and there's code.google.com/edu. I'll tell you a little bit about each of these. The OWASP I mentioned, there's a chapter pretty much almost every major city. They produce this top 10 list of every year what are the top 10 vulnerabilities. I provided some examples of their top 10 list. You can see that their top 10 list has evolved from 2004 to 2007. It's become much more scientific, and they're getting better with the categorization, which is great to see. Security Focus is the home of the bug track mailing list, where vulnerability reports are mailed out. I'd encourage you to check that out. There's lots of different focus areas for you to check out there. Finally, last but not least, there's code.google.com/edu, where we've started offering free information so that if you need to teach a security course or you want to get a group together to learn security, you can just download free materials off of this website. Let's see. So I just want to conclude. What should you take away from this talk? Every software engineer should also be a software security practitioner. Joel might have mentioned that I work at Google. We're looking for smart people to help us with application security and botnets. There's lots of interesting problems to solve. We'd love to give you the opportunity to help us solve some of them. All of the resources that I mentioned in this talk are available at learnsecurity.com. One other thing that's available there is there are slides corresponding to each chapter of my book, Foundations of Security, so that if you need to teach courses quickly, you can go ahead and get that. Let's see, if you have any questions or you'd like to learn more, feel free to drop me an email and or visit my website. And I'll conclude there. Hope you've found this informational. I'd be happy to take questions offline. Questions?
Any questions for Dr. Deswani?
Okay, well, in that case, I'm going to go ahead and raffle off a book then. I know it's probably a whirlwind worth of information. Let's see, so since I'm out here today and representing Google, I thought I might ask a trivia question about Google, and the person who answers it will get a copy. Let's see, can anyone name or tell me which Google vice president used to own the garage that Larry and Sergey first started working in? Oh. No, it's not Omid Kordestani. Omid is our Vice President of Business Development. There is another Google VP that hosted them in their first garage. No? Okay. I can do another question. So let's see. How about... okay. Can someone name 3 of Google's angel investors? Can someone name 1 of Google's angel investors? Can someone name 1 of Google's investors? Forget angels. In the back? Joel Birnbaum. I'm not quite sure. You think he invested? Okay. I'm not familiar with him, but I'll go ahead and give you a book since you tried. Other investors include Andy Bechtolstein from Sun, David Sheraton from Cisco and Granite Systems. Let's see. Kleiner Perkins was the VC that invested in Google. So anyhow, feel free to come up and collect your book, and I'd be happy to take questions online. And or if you're interested in learning more about job opportunities at Google, feel free to come talk to me and or drop me a note with your resume.